So thankfully, yes, there is an equation to relate delta G with equilibrium constant. And so here it is. So in this case, delta G is equal to negative RT ln K. So a couple of things to be careful with this equation. First off, the R for this equation is not the gas R. Instead, it's the ratio between energy and the moles and Kelvin. So the number that we're going to use is 8.314. This number is given to you on your AP equation packet, so you don't necessarily need to memorize it, but you need to make sure that you're matching the right R with the right equation. And the reason we're using this particular R is because delta G is in joules per mole, so there's the matchup with joules, temperature, Kelvin, and we've got the moles right there. And so it's in order to make things line up so that they cancel out appropriately. If you're to use the 0.0821 liters atmospheres moles Kelvin, there's no atmospheres anywhere in this equation, so it's a signal to you that it's not the right one. And as usual, temperature needs to be in Kelvin. And then this right here is just the rearrangement of this equation solved, and it's because we have that natural log in there. So if we solve for K, we use the inverse natural log, which is the little E button. It's not the same as the EE button, the times 10 scientific notation one. It's a lowercase e. So on the AP test, you are not given a calculator on the multiple choice part. Doesn't mean there's no calculations on the multiple choice part. It means you have to be able to make estimations. So let's talk about how to estimate E then. So if E is raised to a negative number, whatever it is, that value is going to wind up being less than 1. And the larger the negative number, or the larger in magnitude, so the bigger n is, the more less than 1 it's going to be. So the smaller the number will be. And if E is raised to a positive number, that value is going to be greater than 1. And the larger that number is, the higher above 1 it's going to be. And why is that significant? Because remember, we can also think about K in terms of 1. So if K is less than 1, or if K is greater than 1. And so if a K is less than 1, that means reactants are favored. If a K is greater than 1, that means products are favored. So a good example of a question you might see on the multiple choice section would be one where they give you the delta G value, and they tell you it is, X, and they say, hey, who's favored at equilibrium, products or reactants? And then you would have to make an estimation to figure that out. And something else we can do is like RT, you're going to be given the temperature, and like if you're told the temperature is 298 Kelvin, hey, don't be afraid to round that then in your head to 300 Kelvin, make it a little bit easier to multiply. 8.314 is the R constant, you should know that, but don't be afraid to get rid of that 0.314, and so then really, for this particular question, it'd just be as easy as multiplying 8 times 300 to get your RT value. And that's going to be, 2,400? And so then you would just look at your delta G value, compare it to this one right there, keeping in mind that those two are divided, and it's going to be the negative. And so then you would just think of your E's then. Is it going to be greater than 1, less than 1? Is it going to be a lot greater than 1, or a lot less than 1? Another way you can memorize this is just based upon this little table right here. So if delta G is greater than 0, a positive number, that means it's non-spontaneous. And so that means it's going to be mostly reactants then if it's non-spontaneous. And if it's mostly reactants, KEQ is less than 1. If it is a positive 20 or greater, that means it's going to be virtually all reactants. So very, very few products, which means it's going to be very, very much reactant favored. So KEQ will be significantly less than 1. And if it's a negative number, mostly products. But if it's less than negative 20, it's going to be virtually all products. So very, very few reactants left. Here's an example of an AP multiple choice test question. So this would be one where you do not get a calculator. You would get a periodic table, and that is it. So everything else is going to have to be things that come from your head. So why don't you go ahead, read through this question, pause the video, and give it a shot. I mean, really give it a shot. Take some time, see if you can do this, think through what we know about enthalpy, entropy, Gibbs, and equilibrium. And you can use scratch paper, so you can do calculations written there. Just don't use a calculator for this. Alright, so here's how I'm going to work this out. Delta G equals delta H minus T delta S. And Gibbs, we're going to estimate it. So negative 2,000, that's put into joules. And since this is at standard state, which means 298 Kelvin, I just rounded it up to 300 to make it nice and easy to multiply in my head. And then this can be kept as negative 100 because it's already in joules. And this way all of our units match up. So these two together are going to give me about 30,000. and then that's going to be a positive number, negative times a negative, and then I'm going to have negative 2,000 right there, so negative 2,000 plus 30,000, that's going to give me a grand total of 28,000, and that's just going to be in joules. Okay, so it's AP test time. You're sitting there. If you can remember that chart that we saw a few slides back, you're going to remember that if it is in kilojoules, and so that's going to be 28 kilojoules. And we said that if the kilojoules is greater than 28, it's going to be significantly less than 1, which means it's going to be mostly reactants. So right there, that's going to be D. However, several months later, you're sitting on the test. You don't remember that table anymore or the numbers that were on it, so we've got to use that E. All right, so E then, it's going to be K is equal to E raised to the delta G divided by RT, and that's going to be negative. And our R, that's 8, our T, that's 300, so that number down there is going to be 2,400. And then our number on top, that's going to be the 28,000. So let's see, two of those zeros are going to cancel out. So 24 divided by 280, 280 divided by 24, that's going to be greater than 10. So we know that our E value will be, or our E raised to, a value that's greater than a negative 10, which means it's going to be significantly less than 1. And so once again, we're finding out that K is going to be much, much less than 1. And so if we go back to our multiple choice then, it's going to be D. The system contains mostly reactants. I'm sorry, E, virtually all reactants. So the system contains virtually all reactants. All right, now bust out your calculators and let's do one with actual numbers. So here's our example. We're going to do sulfur dioxide reacting with oxygen to form sulfur trioxide, and this is at equilibrium. So the values that we're given are our enthalpy, our entropy, and it wants to know what Kp is. But wait, Mr. Jones, we weren't given an equation to find equilibrium based upon enthalpy and entropy. No, we were not, but we can use those two values right there again to find our Gibbs free energy, and then we can use our Gibbs free energy to find the equilibrium. All right, so let's work our way through this one then. So here's our equation. Now we need to plug our numbers in. Hey, and let's keep in mind now, we need to switch this over there to joules. The reason we're switching that one to joules and not this one to kilojoules is because our R, which is coming later, is also in joules. And so rather than switching two things, let's just switch one. So then we can plug our values in there. You should be doing this along. And so we get our delta G then to be negative 142,000 joules. And this is much, much less than, or much, much larger than negative 20 kilojoules. So therefore, we know that this is going to be lying very, very far to the right. So products are going to be favored in this reaction. Okay, so let's solve for Kp then. So Kp, E, and in this case, we've got our delta G. It was the negative 142. And then we can plug in our R and our temperature. And just fail-safing, we see that joules is going to cancel out joules, and then moles is going to cancel out moles, Kelvin, Kelvin. Perfect. So then we're left with a nice unitless equilibrium. And so plug it all in, and Kp is going to equal 7.78 times 10 to the 24th. So yeah, a very, very positive number. That means equilibrium is going to lie far to the right, as we would expect from the delta G value that we had.